Here is the full script. Voyager 1 launched in 1977. It has been flying continuously for nearly half a century, covering more than 24 billion kilometers. It is the most distant human-made object in existence, and it has not left the solar system, not by the definition that actually matters. That fact alone should reframe everything you think you know about what escaping the solar system means, because when most people hear that phrase, they picture something manageable. A long trip, sure. A generation, maybe two. A sufficiently powerful rocket, a brave crew, and enough fuel to punch through whatever invisible line marks the end of our cosmic neighborhood. That picture is wrong in almost every way it can be wrong. The solar system is not the 9 planets you memorized in school. It is not even the Kuiper Belt, where Pluto drifts in the dark. The true gravitational boundary of our solar system, the Oort cloud, extends nearly a quarter of the way to the nearest star. We are not talking about a long road trip. We are talking about a distance so vast that it breaks every analogy you try to throw at it. For centuries, humans have looked up and assumed the stars were waiting. That ambition is legitimate. It is the same drive that pushed sailors off the edge of known maps, that sent astronauts to the moon on technology less powerful than your phone. Space agencies talk seriously about Mars missions. Billionaires fund rocket companies with interstellar ambitions written into their founding documents. Science fiction has spent decades telling us that the solar system is a starting point, a launch pad, the first step on a journey that ends somewhere extraordinary. And there is something genuinely moving about that belief. The desire to reach further is one of the better things about us. But desire does not negotiate with physics. Here is the first number you need to sit with. The heliopause, the point where the sun's solar wind loses its influence and interstellar space technically begins, sits roughly 120 astronomical units from Earth. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. Multiply that by 120. Voyager 1 crossed that boundary in 2012, 35 years after launch, traveling at roughly 61,000 kilometers per hour. That is faster than any crewed spacecraft ever built. At that speed, it took 35 years just to reach the nearest agreed-upon edge of our solar system. Not the Oort cloud, just the heliopause. The Oort cloud itself is estimated to begin somewhere between 2,000 and 5,000 astronomical units out, and its outer edge may stretch to 100,000 astronomical units, nearly 1.87 light-years from the Sun. To cross through it entirely and emerge on the other side into true interstellar space would require traveling roughly 2 light-years. At Voyager's speed, that journey would take approximately 37,000 years. To put that in a frame your mind can actually grip, 37,000 years ago, anatomically modern humans were painting cave walls in France. Agriculture did not exist. The wheel had not been invented. Entire civilizations rose and fell 10 times over in that span, and your spacecraft would still be inside the solar system. That is not a technological problem you can iterate your way out of. It is a scale problem, and scale does not care about your ambition. The obvious response is speed. Go faster, build a better engine. And here is where the technology wall appears, and it is vertical. Chemical rockets, the kind we use today, the kind that have taken every human being into space, are limited by the energy density of their propellant. The most efficient chemical engines we have ever built reach exhaust velocities of around 4.5 kilometers per second. That is the ceiling for that technology, not a milestone on the way to something better. Ion drives, which power some robotic probes, are more fuel efficient but produce almost no thrust. They are good for slow, steady acceleration over years, not for cutting 37,000-year journeys into something survivable. Nuclear propulsion could theoretically push a spacecraft to perhaps 1 or 2% of the speed of light. That sounds promising until you run the numbers. 1% of the speed of light is still 3,000 kilometers per second. At that speed, crossing the Oort cloud would take something in the range of 200 to 600 years, still multiple human lifetimes. Still impossible to crew without generational ships, suspended animation, or some biological workaround we have never demonstrated in practice. And nuclear propulsion at that scale requires fuel masses and engineering tolerances we have never come close to achieving. Theoretical drives, fusion engines, antimatter propulsion, Bussard ramjets exist on paper and in journals. They also require either fuels we cannot yet produce in usable quantities, or physics we cannot yet control, or energy densities that dwarf anything our civilization currently generates. Antimatter, for instance, costs billions of dollars per microgram to produce. A crewed mission using antimatter propulsion would require quantities that are not just expensive to manufacture. They are currently impossible to store without annihilating themselves and everything around them. Each proposed solution carries its own wall. And even if you solved the engine problem, even if you could get a crew up to a meaningful fraction of the speed of light, the human body would betray you long before the journey ended. In microgravity, the skeleton begins losing density at roughly 1 to 2% per month. That is not a slight degradation. After 2 years in space, an astronaut's bones can resemble those of a person decades older, brittle in ways that physical therapy can partially address but never fully reverse. The muscles follow. Leg muscles, back muscles, and critically the heart, which is itself a muscle, begin to atrophy. The heart, no longer working against gravity, physically shrinks. It becomes less efficient. Blood redistributes toward the upper body, which the brain interprets as excess fluid and responds to by reducing overall blood volume. When the crew eventually tries to stand, their cardiovascular system cannot compensate fast enough. They pass out. The eyes go next, and this one is harder to prepare for. Intracranial pressure increases in microgravity, pressing against the optic nerve from behind. The eyeballs themselves change shape. Studies of astronauts returning from long-duration missions have found structural changes to the eye that, in some cases, do not fully reverse. Permanent vision loss is a documented risk of extended spaceflight. Then there is radiation. Beyond the magnetosphere, beyond any planetary protection, a crew would be exposed to galactic cosmic rays, high-energy particles traveling at near-light speed themselves, capable of passing straight through spacecraft walls and straight through human tissue. They break DNA strands, they damage neurons. There is no shielding material we currently possess that blocks them effectively without adding so much mass that the spacecraft becomes impossible to launch. A long-duration deep space crew would be accepting a cancer risk and a neurological degradation risk that climbs steadily with every year of travel. Not a risk you accept once, a risk that compounds daily for decades. These problems do not stay separate, they interact. A crew member with degraded vision and reduced cardiovascular capacity is less able to perform the physical repairs a spacecraft inevitably needs. A crew member experiencing radiation-induced cognitive decline is less able to troubleshoot the life support failures that deep space isolation and micrometeorite damage will eventually cause. The communication delay to Earth, which grows from minutes to hours to days as the ship moves outward, means that mission control cannot help in real time. The crew is alone in a way that no human being has ever been alone, making complex decisions with degraded biology and no backup. Water recycling fails incrementally, spare parts run out. Psychological fractures develop in isolation that no PTARs. Psychological screening process can fully predict, and all of this is happening while the destination, the actual edge of the solar system, is still centuries away. With current technology, a crewed mission to escape the solar system entirely within a single human lifetime is not an engineering challenge waiting for a bigger budget. It is a collision with the fundamental constraints of physics, biology, and energy. The distances involved require either speeds we cannot generate or timescales that exceed human life. The biology required to survive those timescales does not match the biology we actually have. The energy needed to solve the speed problem exceeds anything our civilization currently produces. This is not pessimism, it is arithmetic. What we have managed to do, though, is remarkable in its own right. We built Voyager 1 in the 1970s, hardware designed before personal computers existed, and it is still transmitting data from beyond the heliopause. The signal takes more than 22 hours to reach us. The team that communicates with it uses frequency references from an earlier era, and decades-old software kept running specifically because nothing newer is compatible with a spacecraft that should not, by any reasonable expectation, still be working. We sent that machine into the dark, and it is still talking to us. We may not cross the Oort cloud in our lifetimes, or in the lifetimes of anyone alive today. The solar system is not a neighborhood we are equipped to leave on any human timescale with any technology currently in existence, or on any credible near-future roadmap. But we have already touched interstellar space, with instruments, with mathematics, with the accumulated effort of thousands of people who understood the scale and decided to try anyway. That is not a consolation prize. That is genuinely one of the most extraordinary things our species has ever done. We built something that outlived its creators and kept going,